Good morning, everyone. This is Dr. G. Anita. I'm Assistant Professor in the Department of EECE. Today, I'm going to discuss about satellite communications. So in satellite communications, we have 5 modules. And in this video, mostly we are going to discuss about some of the topics from module 1. So in module 1, as it is shown here, we have some topics by the name elements of orbital mechanics. So first topic is equations of motion, tracking and orbit determination, orbital correction, control, satellite launch systems, multi-stage rocket launchers and their performance. So in the first module, we are going to study about the elements of orbital mechanics. So how a satellite orbit will be and what are the different orbital perturbations, orbital elements, all these we are going to study here. Along with that, the tracking system, satellite launch vehicles, all these we are going to discuss here. Now, we are having so many topics in the first unit. So in this particular video, I'm going to cover some of the topics related to first unit. So the contents in my presentation is Introduction to Satellite Communications, then Satellite Services, then Earth Orbit Satellites, then Kepler's Laws, and finally Orbital Elements. Coming to the Introduction to Satellite Communications. So first of all, what is meant by communication? Communication is nothing but it is the exchange of information between the transmitter and the receiver. For example, if I am the transmitter and if I am transmitting a message, then the listener will be the receiver. Now coming to satellite communications. Here, what is meant by a satellite? Now, what is a satellite? A satellite is nothing but it's a huge body that moves around another body in a mathematically predictable path. And this path we call it as an orbit. Now, when two stations on the earth want to communicate through a radio broadcast but are too far away to use the conventional means. Generally, in order to connect a transmitter and a receiver, we'll be using some communication means the medium of propagation between the transmitter and the receiver. So like microwave links, coaxial cables, optical fibers, all these are some communication, means the physical links which connects the transmitter and the receiver. Now here in satellite communications, if we want to connect two stations on the earth which are separated very far away, so how can we connect these two stations? So it can be done by using a satellite. So here, the two stations can use a satellite as a relay station for their communication. So this is the diagram for satellite communication. If you observe this diagram, here we are having a satellite, first Earth station, second Earth station, and the link between first Earth station and satellite is uplink, and from the satellite to the second Earth station is downlink. So here, one Earth station sends a transmission to the satellite. So if you observe in the diagram, the first Earth station sends a signal to the satellite. Okay, this we call it as uplink. And the process of transmission from the first Earth station to the satellite, we call it as uplink. And the frequency that we use here is called as uplink frequency. And the satellite transponder will convert the signal and sends it down to the second Earth station. Now we call this process as downlink. And the frequency here that we use for downlink is downlink frequency. Now let us see some of the advantages of satellite communication. So satellite has several applications and several advantages. So the main advantages of satellite communication are the coverage area of the satellite greatly exceeds that of a terrestrial system. So what is meant by this? Here, if you take any communication means for example, if you take a microwave link, it will cover only a certain area. Similarly, if you take an optical fiber, it will also cover some area. Whereas a satellite, since it is placed in the space, it will cover a huge area. So the coverage area of the satellite is very high when compared to any other terrestrial communication system. Okay, so that is the first advantage. The second advantage is the transmission cost of the satellite is independent of the distance from the center of the coverage area. So here, since the satellite is covering a huge area, it is not the transmission cost, it doesn't depend upon the distance. That is, it is independent of the distance. So that is one more advantage of satellite communication. Coming to the third advantage, the satellite to satellite communication is very precise. And lastly, higher bandwidths are available for use. So along with advantages, the satellite communications has some disadvantages also. So first disadvantage is the initial costs such as the segment cost and the launch costs are very high. And the second disadvantage is the congestion of frequencies. And last disadvantage is the interference and propagation delay. So these are some of the disadvantages of satellite communications. Next, let us see some of the applications of satellite communications. So satellite communications has huge applications. So it can be used for radio broadcasting, TV broadcasting such as DTH, direct to home. Then in an internet applications such as providing internet connection for data transfer, GPS applications, internet surfing, etc. And it can be also used for voice communications. It can also be used for research and development sectors in many areas. And finally, it is used in military applications and navigation. Coming to the second topic, that is satellite services. So here the satellite services are classified into three types. So first one is fixed satellite services, second is broadcast satellite services, and mobile satellite services. So what is meant by fixed satellite services? Mostly it is known as FSS. So it is defined as a radio communication service between the Earth stations at given positions. Means when one or more satellites are used. Now, what is this given position? The given position may be a specified fixed point or any fixed point within the specified area. Next is broadcast satellite service. So it is mostly known as BSS. So it is defined as a radio communication service in which the signals transmitted or retransmitted by the space stations are intended for direct reception by the general public. Means directly it is received by the general public, direct to home applications. Next, third is mobile satellite services. It is abbreviated as MSS. Now, mobile satellite services, it refers to the network of communication satellites intended for use with mobile and portable wireless technologies. So these are the three satellite services we can see. And coming to the next one, that is frequency bands. So what are the frequency bands that are used in satellite communications? So depending upon different kinds of satellites, we'll be using different frequency bands. So what are these frequency bands? Generally, the microwave frequency bands range is L, S, C, X, Ku, K, Ka bands. Okay. So these are the bands generally used by the satellite also. For satellite communication also, we'll be using these frequency bands. Now, L band, as we know, the L band frequency range is 1 to 2 gigahertz. And mostly it is used by the mobile satellite services. Coming to the second one, that is S-band. S-band is, the frequency range of S-band is 2 to 4 gigahertz. And mostly it is used by the mobile satellite services. And also along with that, it is also used by NASA and deep space research. Then coming to the third one, that is C-band. The frequency range of C-band is 4 to 8 gigahertz. And mostly it is used by FSS. Then fourth one is X-band. The frequency range of X-band is 8 to 12.5 gigahertz. and it is also used by fixed satellite services. Okay, and the examples are military and meteorological satellites. Then coming to Ku band, the frequency range of Ku band is 12.5 to 18 gigahertz, and mostly it is used by FSS and also broadcast satellite services. Then coming to K band, the frequency range of K band is 18 to 26.5 gigahertz. It is also used by FSS and BSS. And lastly, Ka band. The frequency range of Ka band is 26.5 to 40 gigahertz, and mostly it is used by FSS. So these are the different frequency bands used by the satellite communications. So different kinds of satellites will be using these different frequency bands. Not all the satellites will be using the same frequency band. Coming to Earth orbit satellites. Now, the satellite is placed in the space. Okay. Now, what happens? It is placed in space, and the satellite path. In the previous slide, we have seen the satellite path is nothing but it is represented as orbit. Okay. So here we are going to see Earth orbit satellites. So satellite should be properly placed in the corresponding orbit after leaving it in the space. Now, it revolves in a particular way and serves its purpose for scientific, military, or commercial applications. The orbits which are assigned to satellites with respect to the Earth are called as Earth orbits. And the satellites present in those orbits are called as Earth orbit satellites. So there are three important types of Earth orbit satellites. So first one is GEO, mostly known as GEO. Then MEO means MEO, and lastly LEO. So what is meant by GEO? GEO is nothing but geosynchronous Earth orbit satellite. So what is this geosynchronous Earth orbit satellite? It is a satellite. It is an orbit which is placed at an altitude of 22,300 miles above the Earth. This orbit is synchronized with a sidereal day. Means a sidereal day is 23 hours 56 minutes. And this orbit can have inclination as well as eccentricity. It may not be circular, means the orbit may not be circular. This orbit can be tilted at the poles of the Earth, but for appearance, it appears as if it is stationary. So it appears stationary when observed from the Earth. These satellites are used mostly for television communication. So the same geosynchronous orbit, if it is circular, so geosynchronous orbit is not circular. If it is circular and in the plane of the equator, then it is called as geostationary orbit. These satellites are placed at 35,900 kilometers, same as geosynchronous, above the Earth's equator, and they keep on rotating with respect to the Earth's direction. The satellites present in these orbits have the angular velocity same as that of the Earth. So these geostationary orbits, in these, whatever the satellites that are placed, they will be having the same angular velocity as the Earth. Hence, these satellites are considered as stationary with respect to the Earth, since they are in synchronous with the Earth's rotation. The advantage of geostationary orbit is that there is no need to track the antennas in order to find the position of satellites. And geostationary Earth orbit satellites are used for, mainly they are used for weather forecasting applications, TV applications, radio, and other global communications. So if you see this diagram here, you can see the geosynchronous orbit and geostationary orbit. So geostationary orbit is along the equatorial plane, and geosynchronous is, it is not along the equatorial plane. Next, second one is medium Earth orbit satellites, MEO. So the medium Earth orbit satellites will orbit at a distance of about 8,000 miles from the Earth's surface. So signals transmitted from a MEO satellite travel a shorter distance. Due to this, since they travel only shorter distance, what happens is the signal strength at the received end will get improved. This shows that the smaller and lightweight receiving terminals can be used at the receiving end. So medium satellites mainly will orbit at distance of about 8,000 miles. Coming to the last one, that is low Earth orbit satellites, LEOs. So low Earth orbit satellites are mainly classified into again three categories: little LEOs, big LEOs and mega LEOs. Now LEOs will orbit at a distance of 500 to 1000 miles above the Earth's surface. Okay, so the range is, depending upon little to mega LEOs, the range is considered as 500 to 1000 miles above the Earth's surface. And these satellites are mainly used for satellite phones and GPS. So you can see the three Earth orbits here. So center is Earth. In the brown color, whatever the orbit, the path that is shown, the orbit is nothing but LEO. The brown color one is LEO. The blue color one is nothing but MEO. And the dark green color is nothing but GEO. So coming to next topic. So as an introduction to the orbital mechanics, let us see some orbital equations. So forces acting on the satellite. A satellite, when it revolves around the Earth, it undergoes a pulling force from the Earth due to the Earth's gravitational force. This force, we call it as centripetal force, because this force tends the satellite towards it. And mathematically, we can represent the centripetal force acting on the satellite as, here we are considering as, the centripetal force is represented with F1. So F1 equal to capital G M into small m divided by R square. Now what is this capital G? Capital G is nothing but universal gravitational constant. Capital M represents the mass of the Earth. Small m represents the mass of the satellite. And capital R represents the distance from the satellite to the center of the Earth. So centripetal force is represented with, mathematically represented with F1, and it is given by Gmm by R square. A satellite, when it revolves around the Earth, it undergoes a pulling force from the sun as well as moon due to the gravitational forces. So this force is called as centrifugal force, because this force tends the satellite away from the Earth. And centrifugal force is represented by F2. So F2 is given mathematically as mv square by r. Now small m represents the mass of the satellite. Here r represents the distance between the satellite and the Earth's center, and small v, here you can see the small v represents the orbital velocity of the satellite. Okay, here we are introducing a small new parameter, that is orbital velocity of the satellite. So what is orbital velocity? So orbital velocity of the satellite is the velocity at which the satellite revolves around the Earth. So satellite doesn't deviate from its orbit and move with certain velocity in that orbit only when the centripetal and centrifugal forces are balanced. So we are equating centripetal force and centrifugal force, F1 and F2. So after equating, we are getting the orbital velocity, small v, as root over gm by r. So the orbital velocity mainly depends upon the two constants, means the gravitational constant and the mass of the Earth. These two are constants. So it is so the orbital velocity, since it is dependent on only these parameters, and from this expression we can say that it is dependent upon G, M and R. Since G and M are constant, it is only dependent on R. So it is the orbital velocity depends upon the distance from the satellite to the Earth's center. That we can conclude from this particular expression. Okay. So it depends upon the orbital velocity depends upon the distance between the satellite and the Earth's center. So we know that the satellite revolves around the Earth, which is similar to the Earth revolves around the Sun. So the principles which are applied to the Earth and its movement around the Sun are also applicable to the satellite and its movement around the Earth. Many scientists have given different types of theories from early times, but only the Johannes Kepler, who lived in the period of 1571 to 1630, was one of the most accepted scientists in describing the principles of satellite that moves around the Earth. So Kepler formulated three laws that changed the whole satellite communication theory and observations. These are popularly known as Kepler's laws, and these are helpful to visualize the motion through space. So three laws are there, which is given by Kepler's. So Kepler's first law. So what it states? It states that the path followed by the satellite around its primary. Here the primary object is Earth. So the path followed by the satellite around the primary will be an ellipse. So he concluded that the path followed by the satellite around the Earth is an ellipse. It is in elliptical shape. So this ellipse has two focal points, F1 and F2. If you observe the diagram, you can see F1 and F2. So what are F1 and F2? F1 and F2 are two focal points on the ellipse. So here you can see the major axis and minor axis. So you can also see small a and small b. So what is small a and small b? Small a is half of major axis and small b is half of minor axis. So the center of mass of the Earth will always be present at one of the two foci of the ellipse. Now, if the distance from the center of the object to a point on its elliptical path is considered, then the farthest point of the ellipse from the center is called as apogee and the shortest point is called as perigee. Okay, now what we are saying? We have defined two parameters here. One is apogee and second one is perigee. So farthest point is apogee and closest point or shortest point is perigee. Here we are also defining one more parameter, that is eccentricity. It is represented with E. Eccentricity of this system can be represented as square root of a square minus b square by a, where what is meant by a and b? A and b are the lengths of semi-major axis and semi-minor axis respectively. Coming to the second law. So what is the first law? The path followed by the satellite around the Earth is ellipse. Okay. Coming to the second law. So what is the second law? What it states? It states that for equal intervals of time, the area covered by the satellite is equal with respect to the center of the Earth. So if you see here in this diagram, you have small p1 and p2. So these two are two distances. P1 and P2 represents two distances, which covers B1 and B2. B1 and B2 are nothing but two areas. Okay. So what is the definition of Kepler's second law? It states that for equal intervals of time, the area covered by the satellite is equal with respect to the center of the Earth. Suppose, here you can see, suppose that the satellite covers P1 and P2 distances in the same time interval, then the areas B1 and B2 covered in both instances respectively are equal. So the areas covered B1 and B2 in these time instances are equal. Coming to third law, Kepler's third law. So it states that the square of the periodic time of an elliptical orbit is proportional to the cube of its semi-major axis length. So mathematically we can represent as the square of the periodic time of an elliptical orbit. Okay, So this time is represented with capital T. So T square is proportional to A cube. So it is proportional to cube of semi-major axis length. So here semi-major axis length is represented with A. So T square is proportional to A cube. Or we can write T square is equal to 4 pi square by mu into A cube. Now what is this 4 pi square by mu? It is called as proportionality constant, where mu is nothing but Kepler's constant. Now, finally, we can represent the value of semi-major axis, small a, in terms of mean motion of the satellite, which is represented with small n. So, a cube is equal to mu into n square. We can represent in terms of mean motion of the satellite n, the value of semi-major axis in terms of n as a cube is equal to mu into n square, where n is the mean motion of the satellite in radians per second. The path of the satellite revolving around the Earth is known as orbit. So this path can be represented with mathematical notations. Now what is orbital mechanics? It is the study of motion of the satellites that are present in orbits. So we can easily understand the space operations with the knowledge of orbital motions. So coming to orbital elements. So orbital elements are the parameters which are helpful for describing the orbital motion of satellites. Now there are 6 orbital elements. So first one is semi-major axis. Next is eccentricity. Third one is mean anomaly. Next, fourth one is augment of perigee. Fifth one inclination. Sixth one is right ascension of ascending node. So first one is semi-major axis. So if you see this diagram, already this diagram we have seen previously. The same diagram is represented here. Here we are going to study about the semi-major axis. So what is orbital element? Now here I told there are 6 orbital elements, and these 6 orbital elements will be giving some information. So first one is semi-major axis. So semi-major axis, what it gives? The length of semi-major axis, small a, represented with small a, it defines the size of the satellite's orbit. So what it gives? It gives the size of the satellite's orbit. We know we have a satellite orbit will be there. Now, what is the size of that particular orbit will be given by the semi-major axis. So semi-major axis is nothing but it is half of major axis. This runs from the center through a focus to the edge of the ellipse. So it is the radius of an orbit at the orbit's 2 most distant points. So here in the diagram you can see semi-major axis. At the bottom you can see semi-major axis. The length of semi-major axis not only determines the size of the satellite's orbit but also the time period of revolution. If circular orbit is considered as a special case, then the length of the semi-major axis will be equal to the radius of circular orbit. This point has to be noted. Coming to the second one, that is eccentricity. So what is eccentricity and what it gives? This orbital element, what it indicates? So the value of eccentricity fixes the shape of the satellite's orbit. So previously the semi-major axis will give the size of the satellite's orbit, and here the eccentricity will give the shape of the satellite's orbit. So this parameter indicates the deviation of orbit shape from a perfect circle. If the length of semi-major axis and semi-minor axis of an elliptical orbit are represented with a and b, then the eccentricity is given by root over a square minus b square by a. Already this formula I told previously. Now, the value of eccentricity of a circular orbit is 0, since both a and b are equal. If a and b means semi-major axis and semi-minor axis are equal, if its values are equal, then the what happens? The eccentricity value will be equal to 0. The value of eccentricity of an elliptical orbit lies between 0 and 1. So E lies between 0 and 1. Okay. So here in this particular diagram, you can see when E equal to 0, it is the orbit path is circle. It's like a circular shape. And if E value is increasing from 0, so if E equal to 0.5, the shape is like an ellipse. And if it is still increasing 0.75, again the shape is same. And if E equal to 0.9, so from circle it is changing like an ellipse. So E lies between 0 and 1. Third parameter is mean anomaly. Now what is meant by mean anomaly? It is represented with capital M. So already we have seen in the previous slide what is meant by perigee and apogee. So farthest point is apogee and closest point is perigee. So mean anomaly gives the average value of the angular position of the satellite with reference to perigee. So what it gives? It gives the angular position of the satellite with reference to the perigee. If the orbit is circular, then the mean anomaly gives the angular position of the satellite in the orbit. But if the orbit is elliptical, then the calculation of exact position is very difficult. At that time, mean anomaly is used as an intermediate step. Fourth parameter is argument of perigee. So satellite orbit cuts the equatorial plane at 2 points. So first point is called as descending node and second point is called as ascending node. Now what are these descending node and ascending node? So descending node means where the satellite passes from the northern hemisphere to the southern hemisphere. And second point is ascending node where the satellite passes from the southern hemisphere to the northern hemisphere. Now, why we are talking about descending node and ascending node means the argument of perigee is the angle between ascending node and perigee. So, if both perigee and ascending node are existing at the same point, then the argument of perigee will be 0 degrees. Argument of perigee is measured in the orbital plane of the Earth's center in the direction of satellite motion. So, this you can see here in this particular diagram. So here if you observe, there is ascending node and descending node. So you can see satellite, apogee, perigee. So farthest point from the center is apogee, closest point is, shortest point is perigee. Then you can also see descending node. Then you can also see ascending node. So here you can see equatorial plane, then the orbital plane means orbit, you can see, then line of Aries, all this you can see in this particular diagram. The fifth parameter is inclination. So what is inclination? In this diagram if you observe, here you have two rectangles. So one is represented in gray color and second one is in white color. So white color one represents the orbital plane and gray color one represents the equatorial plane. Okay, and you can see the perigee point and satellite orbit also. Around the Earth you can see the satellite orbit also. Now, what is meant by inclination here? Here you can see in between the equatorial plane and the orbital plane, there is some angle which is represented with inclination. So the angle between the orbital plane and the Earth's equatorial plane is known as inclination and it is represented with small I. It is measured at the ascending node with the direction being east to north. So inclination defines the orientation of the orbit by considering the equator of the Earth as reference. So inclination, what it indicates? It gives the orientation of the orbit. So this element will give the orientation of the orbit. So what is inclination? It is the angle between the orbital plane and the equatorial plane. So there are 4 types of orbits based on the angle of inclination. One is equatorial orbit. Here the angle of inclination is either 0 degrees or 180 degrees. Then polar orbit, angle of inclination is 90 degrees. Prograde orbit and retrograde orbit. So what is prograde orbit? Angle of inclination lies between 0 and 90 degrees. Retrograde orbit, here the angle of inclination lies between 90 and 180 degrees. And last parameter is right ascension of ascending node. So this is the last orbital parameter. So in this diagram, you can see ascending node, the equator, the perigee, orbit, satellite, all that you can see. Okay, here you can see lambda. So the right ascension of ascending node, which is represented with lambda, is the angle in the equator plane taken from the first point of Aries gamma to the ascending node of the orbit. So here in this particular diagram, you can see the lambda. Here it is represented in blue color. Okay, in the red color, you can see gamma. It is the line of, it is nothing but the first point of Aries. Okay, and in blue color, you can see a point at the bottom, which is ascending node. So the angle between this gamma and ascending node is the lambda. Okay, so right ascension of ascending node, lambda is the angle in the equator plane taken from the first point of Aries to the ascending node of the orbit in clockwise direction. Okay, in counterclockwise direction, that you can see here. Okay, so that is right ascension of ascending node. So these are the 6 elements that you can see. Okay, so these are the 6 orbital elements. So what we have discussed in this particular session, we have seen what is satellite communication. Now, after that, we have seen an introduction to satellite communications. In that, we have seen some frequency bands. After that, we have seen satellite services. Then we have seen Kepler's laws. Then we have seen the orbital elements. Okay, so this part we have covered in our session, in our video today, and we will be covering the next topics in the next video. Thank you.